moment that you lift off into space, the acceleration, the G-forces, that instantly changes to complete freedom when the engines stop. You want to unbuckle and just fly. What you see is the most beautiful thing you ever saw. The planet, it looks extremely peaceful, but it's deceiving to see this and realize all the turmoil that is going on from the weight of humanity.
Franklin has a very interesting history, and he's not just an astronaut, he's somebody who believes in hydrogen and understands the technology very deeply and thinks about the potential of hydrogen to be a part of the solution in climate change.
Most astronauts come back from space with that feeling of a need to protect that one home, the only home we have.
When you think of Cummins, you think of innovation. Countries are looking to reduce their CO2 emissions and to decarbonize their economies. We believe hydrogen and fuel cells can play a key role in making that happen.
Fuel cells that use hydrogen and oxygen to produce electricity for the spacecraft. I envision hydrogen being involved in all power and energy processes on Earth.
Fuel cells have been around for a long time. They got their start in the space program. This is just one more step in the evolution of who we are as a company and what the world demands from its power needs.
Cummins announced a number of investments and partnerships in 2019 in the hydrogen space. We acquired Hydrogenics, which is a company that has leading fuel cell and electrolyzer technologies to make hydrogen. We also announced a partnership with Hyundai to give us access to passenger car type scale fuel cells with metallic plates. And then we also announced an investment in Loop, another company with trapezoid plate channels. Right now, the technology is evolving so much that we want to have optionality, and we want to be sure that we're continuing to evaluate and invest in different technology, potentially for different applications. And now we pair that with the Cummins expertise in other areas. The future is pretty exciting.
We are, as a company, very well positioned technologically. I'd like to think we eventually will be participating in activities on Mars and on the Moon. So a whole universe of possibilities that come along with hydrogen.
Hello everyone, welcome to Tech Talk number 48. My name is Paul Stechik. I'm with NEPSI, Northeast Power Systems, Inc. Today we're going to be talking with Cummins, and specifically Michel Archambault at Cummins. We're going to be talking about green hydrogen. We are going to continue this discussion about green hydrogen. Don't forget, if you want a PTH contact hour certificate for this presentation, either email myself or email Matt Marcet. Please just don't email both of us, and we'll get you that PTH certificate afterwards. So today you might be asking, well, why is NEPSI interested in green hydrogen? The reason is that we sell into the hydrogen supply chain in many different places. We put a circle around those different areas. We sell into the renewables area. NEPSI has capacitor banks, the harmonic filter banks, and now being part of AMSC, we also have the DVAR STATCOM and the VVO STATCOM. All these products supporting the power systems that supply power to the electrolysis plants, pump stations, and so on. So we are a supplier into this supply chain. So that is our interest. NEPSI supplies harmonic filter banks and capacitor banks into this area to support reactive power requirements for the rectifier systems, the electrolysis plants, and also the pump stations. We went through an example with NREL a few weeks ago just to talk about the amount of power required to produce hydrogen. It's not insignificant. The electrolysis facilities require rectifiers. Those rectifiers can consume a significant amount of reactive power. That's what NEPSI produces. That's what AMSC produces, is the reactive power. So that's a picture of what NEPSI produces at that location. Tech Talk 46, we talked about rectifiers. We met with Neotran, Dr. Mauricio Panzetto, great Tech Talk. He touched upon rectifiers and how they're used in the green hydrogen production. Tech Talk 44, we met with NREL, Kevin Harrison. Also another great Tech Talk for you to go back to and check it out. And then, of course, for reactive compensation, we have a whole slew of tech talks. Feel free to go back and look at those. Everything involved with reactive compensation, harmonic filtering. We have plenty of tech talks about that. And all these tech talks are recorded, so go back at any time you want to watch those tech talks. So today we have Michel Archambault with us. Hey, Michel, how you doing?
Very good. Thanks, Paul, for the invitation.
Yeah, so maybe we just start and I'll ask the question. Introduce yourself first, and then we'll talk about Cummins and start your presentation.
Well, thanks, Paul, and congratulations on the platform you're using to produce these tech talks. I've watched the last one with NRL, very professional, very well done, so I appreciate it. I'm Michel Archambault, Director of Business Development and Sales at Cummins. I work in the fuel cell and hydrogen technologies group of Cummins. And if you are familiar with Cummins, we are a large company present worldwide in 190 countries, 60,000 plus employees. We build engines, primarily 1.4 million engines built in 2019. We have multiple distributor and dealer locations. And the two last points are very, very important. Our innovation is really at the root of what we do and what we believe in. So we spend a lot of money on innovation. And I'm part of that group that was acquired in 2019 with Hydrogenics, fuel cells and electrolyzer company. One of the things as well we do is offer a broad portfolio of power solution. And this is really because we support, as I mentioned, innovation-focused path to zero emission for commercial vehicles. And we offer diesel, natural gas. We've also now have hybrid electric, battery electric, and fuel cell electric. And innovation is not only one area. It's not only fuel cells. It's in all these spheres. If we look at the diesel powertrain, for example, we have innovations making more efficient engines. We can use different lower carbon fuels. We can hybridize, and basically battery and electric fuel cells are one way to decarbonize as well. Cummins has 5 business units. Traditionally, they had 4. The 4 first one on the left. I am part of the 5th business segment, which is called New Power. Originally, it was called Electrified Power, but it's been renamed to New Power to incorporate more technologies. As I mentioned, not only one solution is available, it's a multitude of solutions, and fuel cells are seen as one way to reduce emissions and decarbonize hard-to-electrify sectors. The core technologies of our group in the New Power group are the batteries. And these batteries can be used to electrify multiple types of vehicles, either on or off highway, transit buses, school buses, medium-duty trucks, walk-in vans, and so on. But it can also be used in the harder-to-electrify sectors as well. And at one point, it becomes a little bit challenging to use only batteries. And you're looking for shorter refueling time, longer range, as well as lighter weight. And the fuel cell can really play a role there and work hand in hand with the batteries. And Hydrogenics fuel cells were acquired in 2019 and are now part of the mix of Cummins. The last one on the right is the one we're going to be focusing on today, is the hydrogen generation products, which include electrolysis, and we'll talk about 2 technologies, proton exchange membrane, as well as alkaline electrolysis. Paul, you mentioned before our call in the minute when I was waiting in the lobby, why did Cummins really get into electrification, and why did they start the New Power journey? How did that come about? And so it was a strategic decision, and always at the gatekeeping of looking for other solutions. In 2017, officially launched the electrification business development group, and started acquiring primarily battery technologies. In fact, 2 technologies are now part of the portfolio. If you follow the slide from left to right, one is called Bramble, and the other one is Johnson Matthey battery system. We then moved on to how do we put these batteries together and how do we electrify these powertrains, and looked at the company in California that had tremendous expertise in doing that, and acquired EDI, Efficient Drivetrains Inc., which is in Milpitas in the Bay Area. And finally, in July, and I say finally, it's just the beginning, but in July 2019, we acquired General Electric's solid oxide fuel cell technology. I'll not be spending time on that technology, but just to let you know, there's Again, many technologies that can help, and solid oxide is viewed as an efficient way to produce power in the fuel cell, in the different types of fuel cell. Finally, and then it's really finally on the right, we've got the proton exchange membranes and electrolyzers from Hydrogenics that are now part of the mix, as well as some investment in Loop Energy, a fuel cell technology that's gone public recently, based out of Vancouver. And I think there was a small segment that you could see in the video where you saw the Loop Energy, and then you saw the trains using our fuel cells as well. And there was an MOU with Hyundai to collaborate on commercialized electric fuel cell powertrains. Paul, if you have any questions, just please feel free to interrupt at any time. I don't need to go through all the deck. You can stop me at any time.
Yes, I will do so. I'll let you a little bit more continuation on this, and then I'll get you some good questions.
Excellent. And in terms of our footprint, while it's a very new group, only in a year and a half to 2 years old, the New Power Group, we are present in various areas around the world. I'll let you know that we have a facility in Mississauga, Canada, where we make the fuel cells and electrolyzers. The electrolyzers are also produced in Belgium, which shows to be like in Africa now, but it's really not the case. It's just too many letters on that slide. It should be in Europe, of course, and in Germany, where we have a facility making fuel cells. Today it's in Gladbeck, but a month or so ago we announced groundbreaking ceremony where we'll be opening soon a facility in Herten to produce fuel cells and integrate them into powertrains, namely into the Alstom train.
Hey, Michel, I got a couple questions for you. So you're in Quebec, right? You're located in Quebec? Montreal?
I'm close to Montreal, yeah.
Yeah, okay. On your map, you had noted Malta, New York, which happens to be just, I don't know, maybe 20 miles south of us. What's in Malta, New York? Do you know?
I can tell you, I believe it is our SOFC group that is there on the Hydrogen Technologies group.
Okay, all right. I was not aware that you were right there.
That's close to you?
Yeah, maybe 20 miles.
Oh, excellent.
So
excellent. And I went very quickly to these locations. One on the West Coast, one is in the Bay Area, Silicon Valley. That is our integration group, the ones that make these powertrains, bringing batteries and fuel cells to electrify heavy-duty transport, where we make buses and trucks, for example.
Okay.
This slide looks busy, but it's really a good one to go through. The industry is the main consumer of hydrogen. So we'll start from the right side of the screen. Who uses hydrogen today? It's a traditional business. It's a really industrial business, and it's mainly refineries that use it and ammonia producers. And refineries need hydrogen to remove or reduce the sulfur content in their products. And this is absolutely essential as cleaner fuel standards become adopted. The ammonia production is also the second user of hydrogen worldwide. And ammonia is basically nitrogen and hydrogen. And you combine them together, and H, and you form NH3. But if you look on the left side now, where is the hydrogen coming from and how is it produced? Well, it's produced mainly from natural gas and coal, as you can see. So these are the inputs. You're using fossil fuels, which you break down and you crack them using steam and high temperature steam and water easily. And you produce that hydrogen, which will be used for the industries on the right. DRI is the one at the bottom. Is the iron production, direct reduction iron to be precise. And finally, I'm going to go back to the left side where you have byproduct hydrogen. It's a big chunk as well of the hydrogen available worldwide. And this is an example of that would be a chlor-alkali plant, which is really, the purpose is to produce chlorine, but in the process, the byproduct is actually water. You mix the sodium and you mix hydroxide and chloride, and with the water, you produce chlorine and hydrogen as a byproduct in a brine.
Yeah, Michel, might add that we often supply filters into that same marketplace, and the process is similar, right?
And what is the size of these plants, Paul?
The chlorine plants are typically in that 30 megawatt range. A rectifier feeding one cell line about 30 megawatts, and sometimes these plants have multiple cell lines.
It's an electrolyzer basically, but it's a different technology, different electrodes. You're not splitting pure water, you're splitting sodium hydroxide So it's very different technology, which has a different potential as well, cell voltage, I mean. So, and if you look on the left, I put in a box the electricity, and electricity is an electrolyzer, basically how you can produce hydrogen using water and electricity. Split that water and produce the hydrogen and the oxygen, and off you go. But you can see how small the production worldwide of hydrogen via electrolysis is. And so that's a huge potential to start to reduce the carbon content and the greenhouse gases of the hydrogen produced on the left to feed those industrial sectors.
Just 1%, it looks like. So
yeah,
so there's a lot.
6% they say approximately in the reports. And the same thing goes on the right side. You've got transport, which is a tiny line, 0.01, because today there's very little vehicle using hydrogen as a fuel. So fuel cell electric vehicles. You've got cars in California, in Asia, and in Europe, and you're starting to see some buses, but the numbers are not there yet. So it's a huge opportunity to decarbonize and start to increase the chunk of electricity and renewable electricity primarily to decarbonize the sectors on the right.
That ammonia, just to back up 1 second, that ammonia is that used for fertilizer?
Yeah, about 80% of the ammonia produced worldwide, and look at the number, it's MT, it's millions of tons of ammonia that are required, and 80% is used for fertilizer approximately. In terms of the greenhouse gases emission, the ammonia sector is responsible on the planet at a global level for 1.5 to 2%. So it shows you that has a role to play reducing, they call it green ammonia. So to produce green ammonia would already reduce by 1.5 to 2% the emissions worldwide.
Significant.
Yeah, there's other applications like for explosives as well as one of them, and tons of other ones that you can do with ammonia. Going back to transport, there's also, I mentioned regulations in cleaner fuels, but there's also regulations affecting heavy-duty fleets in California, amongst others. There's a new rule, which is called the Advanced Clean Truck Rule, which will ask manufacturers to increase the share of zero-emission trucks between 30 to 50% and 40 to 75 by 2035. And the class is the class of truck. The higher the number, the heavier the vehicle. A class 8 is a semi-trailer, 18-wheel basically that you can see. So in 2035, which is 14 years from now, manufacturers will have to have 40% of their fleet using zero-emission fuel. Right?
And we have our first question from Hugo.
Okay.
So remember, in the chat box, ask questions, and we'll get them answered as we move forward. So Hugo asked a question, is it possible to electrolyze seawater?
Yeah, there's some research being done for that. If you look at what they're doing in the chloralkali, it's a little bit like seawater in a way. It's water and salt. It is possible. Our electrolyzers are not suitable for doing that. There's some material, there's potential. The electrodes are not designed to withstand salt. In fact, we do the opposite. We really remove all the minerals in the water before we put the current and electrolyze it. But there's research being done to do that.
Okay. Good question. Don't forget to ask questions.
Yeah, please. Easy ones, at least. That's for the trucks. I mentioned the class 7, class 8 trucks. A big chunk will need to be electrified or put into zero emission. But we are also doing fuel cell engines that we put on trains, and Alstom takes them and integrates them into their electrified passenger train platform called the Coradia Island. This is really what's happening in Europe. Already 41 trains have been shipped, 82 to be delivered. We've opened that plant. We will be opening soon that plant in Germany to increase our manufacturing capacity there and to be able to sustain the demand. So good things coming up in the train market, and hopefully this will also be a market opening in North America. A slide with no word is always a good slide, but that is an image of a fuel cell truck. It's a fuel cell power truck using hydrogen that we demonstrated about 1.5 years to 2 years ago at a show in the US. So huge potential. A truck like this may consume 30, 40, 50 kilograms, can go even to 90 kilograms depending on how far that truck will go. So you can imagine that as the number of vehicles in the fleet grows, you'll need more hydrogen, and you'll need tons of hydrogen. And better if the hydrogen that is produced is clean, because then you can really address the emissions from production of your fuel into the wheel. We call it well to wheel.
Hey, Michel, we have questions stacking up too. I hate to interrupt you, but it's good to keep them going, and I like the questions. So there's Daniel was asked a question. Daniel Dunner was asked a question. Previous slide data are from 2019, so he had a slide with data on it. Has it changed up to now? Has there been changes?
Is that this slide? Sorry, I can't.
Yeah, I would say so. It was that slide. Did it say 2019?
Yeah, that's the Advanced Clean Truck Rule. That is the one I picked up on that link down at the bottom. So.
Okay. Another question from Dan. He asks, aren't most commuter rails currently electrified? If not, can you talk about the mix of electrical versus other fuels?
Yeah, so it's a good question. I'll talk about the example of Germany. Around 50% of the network is electrified, and you can see that if you take the high-speed train or commuter train from main city to a suburb nearby, and you'll see these catenary wires above the train. And that's full electric. That's not using batteries. It's really just powered by these lines. However, at some point, it becomes very expensive. It's hard to maintain, and there's areas where you can't really put these lines in without so much effort. I shouldn't say any effort, but using basically a regular train, you can retrofit it and put these engines, not have to put the batteries that are too heavy. You make a mix of batteries and fuel cells and use that fuel cell engine to power your train. At the same time, it plays a role of, in the case of Germany, you've got a lot of renewable energies going into the mix. You're at the same time shutting down nuclear, shutting down coal plants, and you'll lose your base load, and energy storage is going to become really important. So if you can produce clean hydrogen and stabilize the electrical grid, then you can power your trains, for example, with that hydrogen. Does that answer the question?
I think so. We got a couple more questions, so this is good. Melissa's asked, when is it expected to be profitable to produce green hydrogen to use it as a fuel in gas turbines?
Very good question. I cannot say exactly when. This is not a question. It's not pure science. There's a lot of policies that need to be put in place before it becomes competitive. One thing I didn't mention on that slide, that chart showing how hydrogen is produced and how it is used, is that you're emitting GHGs when you're producing it. What is the cost of these GHGs today? What will it be in 10 years and 5 years? But the reason it is using fossil fuel is because it's cheaper. So the way we can make it more affordable or closer, we call it diesel, parity with diesel, is to produce more efficient electrolyzers, reduce the total cost of ownership by reducing the capex, reducing the cost of installation, improving the lifetime, and so on. And all these things are driving to the direction of becoming competitive and close to what diesel is.
Probably kind of the way the renewables industry has been moving. I mean, we've been increasing the renewables production, more PV arrays, and the cost has been coming down, right? It's been coming down for the last 20, 30 years. So I would think the same can happen for hydrogen.
Yeah, I do have a slide on that later on that shows that, the real way to go is to get low cost power. And sometimes you're connected to the grid and you can't get that. You're paying for distribution, transmission, and so on. And so the share of renewables and the businesses you can do with the independent power producers will help you get lower costs of power and then produce cheaper hydrogen.
We have a question from Suresh. Is asking, please quantify electricity kilowatt hours required per kilogram of H2 generated. Does this figure depend on the electrolyzer capacity, feed water quality, etc.? So maybe you can touch on that.
I think what I'll do is I'll get there because I have some slides on showing the products and the efficiency, and we can have a better understanding of how that consumes and so on. So I showed you that, and then I'm going to go very quickly over this. Electrolysis is not new in the industry. It's not new for us neither. We've been making it through the companies that are now part of Cummins since 1948. And innovation, again, at the forefront, we started with atmospheric alkaline. This is technology where unipolar technology where you produce your hydrogen without pressure. You're using potassium hydroxide or sodium hydroxide. In our case, it was potassium hydroxide. but we've moved on from that atmospheric technology to a pressurized technology, still alkaline, that we still manufacture today, but for small scale. And in parallel, what's not shown here is when Hydrogenics acquired these electrolyzer companies with that experience, Hydrogenics was a fuel cells company, and I should say a PEM, proton exchange membrane fuel cells company. And all the research and development and all the learnings made in fuel cells can be applied as well to develop our PEM electrolyzer. And that's what's been done for over 20 years. We're now at the point where we're using our PEM to address large-scale production. We'll go quickly to the product portfolio. On the left side, you have our alkaline portfolio. When I say small scale, it's look at the Fort line, 80 kilowatt, 300 kilowatt, half a megawatt, and you can put 2, 3, 4 units depending to reach a couple of megawatts maybe. But at one point it becomes more cost effective, and there's other benefits of moving on to our proton exchange membrane technology. The markets for our alkaline pressurized electrolyzers are traditional. It includes flat glass plant where you're using the hydrogen to prevent oxidation of the tin vat. So when the glass is produced, it melts on the surface on the tin vat, so it's perfectly flat. But if you're just using your natural gas burner to maintain heat, and you have oxygen in that burner, in that furnace, where the tin is, you'll have oxidation, and then the glass will not be of the right shape, will have impurities or defects. So that's why it's used, the hydrogen, just to prevent any oxidation by getting rid of the oxygen. You neutralize the atmosphere. And I'll skip all the other ones, but very traditional industrial processes, including steel, power plant cooling, and edible oils.
Hey, Michel, you want to go back 2 slides and just touch on this for a second? So these are drop-in place, fully unitized systems, right? It contains the input transformer, rectifier, hydrogen fuel, the cells, right, for producing the hydrogen. I assume it's everything combined, right?
Yep. So, all the way up to the HYLYZER 500, the Ford product. They're all, you can have them designed for indoor version, but at that scale, it's also very, I would say most customers opt for a containerized plant. It's easy to install. We supply all the peripheral equipment. And then when you move to the number 3, then it's an indoor version. So I'll show you what it looks like physically. This is just a picture, a rendering, but physically how it's installed in the building. If you want, I can skip right to this one, where your question was it containerized? It is, and the reason is I mentioned as well that it's easy to install, and you have one power supply where you bring the power, customer brings the power to our power supply, which includes a transformer and a rectifier, and then we have another container where we have the electrolyzer that will produce the hydrogen. Going back to the journey that brought us to the larger scale product, larger scale PEM. It's not a short journey, it's 20 plus years into the making with small, very small 10 kilowatt stacks, all the way to now 2.5 megawatt stacks. And that has been a constant deployment. So we've done some testing at our plant before we then shipped our first 1.5 megawatt stack to Germany at the large utility called Uniper, which was part of E.ON. And then we shipped one to Denmark. That's about a 1.2, 1.3 megawatt. And finally, we went to 2.5 megawatt, and now we're at a 5 to 20 megawatt range there. And it's used mainly for different industries that we had before. It's not as industrial so far. It's more used for really supply energy storage options. Power to gas is one of them, where you produce hydrogen and you inject it in the natural gas, producing cleaner natural gas. You can enable mobility. You can also produce cleaner fuels. Top right is a methanol plant. At the bottom is a power to gas plant where we'll be injecting hydrogen in the gas line, but we're also providing grid services, which means we're getting paid to stabilize or stabilize the network. And one in the middle is the one we'll talk about in more details that's been installed and commissioned in Quebec recently. Okay, I think I can go very quickly to the specs. This platform is a 2.5 megawatt. It produces 1.1 ton per day of pressurized hydrogen, and it's containerized. and it includes all the utilities, so water treatment plants, chillers, coolers, AC/DC conversion, and so on.
Hey,
Any questions?
yeah, we got some questions. I have a couple too, but let's get to the chat box first. There's a couple there. I'm going to start from the bottom up. Okay, so let's just start with this one. Is the 2.5 megawatt a single stack or multi-stack system together? Single stack or multiple stack?
Excellent question. It can be done with 2 stacks in this case, so we have a certain redundancy, but the single stack can do 2.5 megawatt. As you'll see in the plant that's double that capacity is using 2.5 megawatt stacks.
So there's a follow-up to that is what is the largest single stack size that you offer for PEM?
It's 2.5 megawatt stack, so it means that it's 2.5, but there's an overdrive. It can go up to 3 megawatt. One thing that I should add for that one, if you have the containerized solution, you can go to a 2.5 megawatt, but you can do it in phases. Some clients look at, we don't have the fleet, we don't need 1 ton per day, but we will need it as the market picks up. We'll add vehicles, or our application will consume more hydrogen. So what they do is they do it in 2 phases. We send 1 stack and 1 power supply, and in phase 2 send the second stack and the second power supply.
Okay.
And then 2.5 megawatt.
Right. The other question is another byproduct of the hydrogen production is oxygen. Do you capture that oxygen and sell that oxygen? Can you comment on that?
We can. The oxygen is pure. We, depending on the application, we would remove the moisture out of the oxygen and capture it. The reality is that most customers, we don't need the oxygen and let it go to vent. But taking in particular one process, methanol production, you need the hydrogen, but you also need the oxygen in some of the process. So you can use both feeds into your plant.
Yeah, Mark had commented perhaps steel, hydrogen peroxide.
Yeah.
Also, Matthew has made a comment. I'm also curious whether these electrolyzer products can be modified to utilize salt or brackish water as an input as part of the water purification process.
Not today. Something to look at, but not today.
Okay. Do you produce and sell 100 kilowatt PEM electrolyzers anymore?
No, we I go back to that slide with our product range. Our largest, our smallest PEM is a 1 megawatt. So that's the one here, actually, 435 kilogram per day. So no, we don't do 100 kilowatt PEM anymore.
So my question was, where does the EPC fit in to these projects? Some of these are drop in place. Where does the EPC fit into it? Okay.
Next slide shows, I talked a little bit about how that's done. We are not an EPC company at Cummins. We are equipment manufacturer. We support our products and service them, but we need EPC companies to install the products. And in this particular case of an outdoor product, you'll need to lay out the concrete foundations, bring power from the grid to our power supply. You'll have the craning and the installation. I can show the other slide. I think you see it more here, where you connect. You have the overhead connections or underground trenching and so on, and that's where the EPC comes in. We make the electrolyzer as easy to install as possible when it's containerized. We bring in the utilities when it's needed. Our customer is free to bring them as well. But the EPC brings it all together, and the construction company makes the site ready for that. And that's for the outdoor version, sorry. But if we go to the, and that looks like a complicated product, but in fact, this one here is just a station where we're producing clean hydrogen, feeding a compressor, feeding some storage. What's cool about it is the trailer comes in and is pressurized with that hydrogen, and then can distribute the hydrogen and sell it to customers in the vicinity. In this case, it's a network of fueling stations. On the indoor version, when we grow in size, it becomes impractical to have like multiple containers. We wouldn't want 40, 50 containers, so we would encourage to go into an indoor solution. That's a 5 megawatt building block. That's the one installed in Quebec. You can see we make them very modular, very easy to install. The role of an EPC in this case would be, again, the same thing: bring the building together, bring the ventilation inside the building, the purge gas, and utilities to make this electrolyzer work. But as I mentioned, we make it very modular and very easy to install to reduce the total cost of installation and of ownership.
Okay.
Any other follow-up?
Yeah, we have other questions, but I think some of them you probably won't answer. They're asking about CapEx and OpEx. I'm not sure if you want to comment on those for the 2.5, but it's a tech talk, so I would say we'll keep it. You can get my email address. Yeah, we'll keep it non-commercial. Okay, so let me make sure we got nothing else. Alkaline electrolyzers are known to have a long lifetime compared to that of PEM electrolyzers. What are the basic driving forces for producing PEM electrolyzers rather than alkaline ones?
One driver is on that slide, the efficiency and the pressure. Our electrolyzers produce hydrogen at 30 bar pressure without any compressor. So you can feed a lot of processes directly at 30 bar or 435 psi. Without that compressor, and if you do need to go higher pressure, well, you skip a difficult compression stage. The second one is efficiency. So first, if you don't have any compressor, you don't have any loss of efficiency there. But the main driver is that our PEM stack is now more efficient than our alkaline stacks. We see a total cost of ownership becoming lower with our PEM, so it is lower already at large scale, and that is not only a CapEx decision, it's a total solution decision. I mentioned installation. Well, installation costs are expensive when you've got a bigger plant. A bigger building will cost more, the concrete will cost more. The flexibility of operation of the PEM is another driver. It's very flexible. It's able to produce to very quickly up and down and doesn't use any chemicals. So there's a lot of drivers, which I think you'll see throughout the presentation. To end on your question about EPC, I've listed utilities or main utilities required here, it being power, cooling water, instrument air, purge gas, calibration gas, and water treatment system. And the water treatment system is really taking potable water, and then we remove all the minerals, we demineralize it, and feed the electrolyzer with that pure water that can go into these stacks that you should see at the forefront here. Or here. So to the question that somebody asked about the size of the stack, well, this one is a 540 kilogram per day stack. That's 250 cubic meters an hour, or if you want, about 1.2 megawatt. And this one is a 2.5 megawatt stack.
Okay, we got a couple of hydrogen questions. Well, how many cells in the 2.5 megawatt stack, if you can answer that, and then you can follow up with a somewhat unrelated question about the advantages of blue hydrogen versus green hydrogen.
Yeah, we don't disclose the number of cells in the stack. And the second follow-up question was?
Blue hydrogen versus green hydrogen.
It's an interesting question.
Advantages.
So there's a lot of discussions and debate around using colors to describe hydrogen. We use green hydrogen because we're using green power to produce it via electrolysis. That's one way to do it. Other ways are what I've shown on the other slide is gray hydrogen coming from fossil fuels. And the blue hydrogen is when you capture the CO2 that is emitted in the production of gray hydrogen. So that's one way to see it. It's very visual, very easy to understand. But the industry is now moving to a different system, and it's not in place, it's not perfect yet. It will be to measure the carbon intensity of the hydrogen. And the reason for that is that as you get a lower carbon intensity, you will get more credits. And then if you're using it for fuel, for example, for the mobility side, you'll have a lower cost of hydrogen because these credits will be larger if you have a cleaner fuel. And if you're producing gray hydrogen, then your benchmark will be against diesel, and then you'll get less credits. So it will be a benefit for you to move on to cleaner hydrogen. And to end on that topic, there's also the reason it becomes complicated is, where does biomass production fit? Is it green hydrogen because the CO2 is considered biogenic, but is not captured in the end? And then you look at nuclear. Is it green hydrogen because there's no CO2? But then you've got the nuclear waste, so then they call it purple hydrogen. So it's an interesting debate that is in progress at the moment.
We have some questions about the the rectifier and voltages, I'll ask you the question. You may or may not be able to answer it, but I will refer people back to a previous Tech Talk where we did have Neotran on that was talking quite a bit about the rectifiers, the thyristor versus diode front end versus the chopper rectifier. So you might want to go back to that, but Eric asked the question, for the rectifier, what is the level of voltage and current? Or does it change depending upon the project?
I think I can go here. So these electrolyzers accept medium voltage power. The range is for anywhere between 4.16 to 30 kV approximately. And that's how we work. So you bring the power to 4.16 to 30 kV. We take care of it at that medium voltage range, and we feed and distribute the power. You see the bus bars here, and we feed the stacks and distribute the voltage, which I won't say, but distribute the voltage evenly across the stacks.
Okay.
And I mean, if you look at harmonics and so on, then you really do need to have a coordination study. Every site is different. If you need filters or not. You, in some cases, a plant like this may have compressors, synchronous compressors, which affect in some way the power factor. In some cases, you're just connected to a renewable energy plant. So really, every site is specific and needs to have its own coordination study.
Incidentally, that's where we come into play, Michel. We provide that other part of the plant, the rectifiers and well, not the rectifiers, but the filters for the rectifiers, and do the harmonic analysis should it be necessary, and then supply filters.
And it was interesting, Paul, when you mentioned when we first got in contact that you were working in projects that we were involved and we didn't know. So it was great to connect. So we work together indirectly in some areas.
Yes.
Yes, it's great.
We have overlap.
Yeah, I can go here to finalize. There's not that many slides left, but this is an example of a project, and one asked about the total cost of ownership and the drivers to go to PEM. This is one of the answers. In this particular case, the building was already there. There was an electrolyzer that we delivered when we were called the ELECTROLYZER Corporation in 1985 or so. And it was a 3-ton per day plant. It was alkaline, and it was taken out by the customer. Our customer is Air Liquide Canada, and that plant is in Quebec. It's a 20 megawatt electrolyzer. So right now it's producing 8.6 tons per day of hydrogen, and it fits in the same footprint and even a little bit smaller. So that's one of the drivers, reduced installation costs in this site. Low cost power was available, and clean power in Quebec. There's another driver. And so that's what it looks like inside the plant.
So it's a scalable product. You're getting to that 20 megawatts with these here?
And as the market grows, today it's the world's largest, and we won't be saying that for a long time, because the industry is really picking up, and the market of refinery, of ammonia, transportation, as I mentioned, are really going to increase the demand for hydrogen, and these projects will become in the hundreds of megawatts. So we are following that demand closely and scaling up our production capabilities worldwide, but also scaling up that HYLYZER 1000 to a bigger plant and address larger capacity needs.
Can you touch on maybe large-scale power generation via hydrogen? Is that something that you can touch on, or will you be touching on it today?
I won't be touching on that, but you mean using hydrogen and burning it in the turbine?
Yes, correct.
So there are projects and discussions. I'm sure if you Google, you'll find a few of the turbine makers that have the same drivers. They need to run on cleaner fuels. And to do that, one of the options is to put more hydrogen into the mix. Some turbine manufacturers say that they can go up to 30% and eventually will go to 100% hydrogen, and therefore not generating any GHGs anymore. So we're not a turbine manufacturer, but it's a market that could be using vast quantities of hydrogen.
Okay, thanks.
Okay, that's a layout. I can skip that. I mean, it just shows how quickly, and you can see the rectifiers. It looks pretty much like that at the plant in Quebec. And you can see on the right side, there will be, depending 1, 2, 3, 4 cooling towers, depending on the size, but you typically have an EPC design the best solution, and that's why it's in pink, or optional supplied by Cummins or supplied by the EPC. Okay. I mentioned one of the drivers was the efficiency of our plant is really improving. We're extremely efficient, 82% at the stack level, at nominal, and in the high 90s. And when we run that plant at a very low current density, because that's how it works. The lower current density, the higher efficiency, but the downside is that you're not producing a lot of hydrogen, but your efficiency is great. So you have to find the right balance. And if you look at the in Canada and in the United States, I've taken a map of power prices just to illustrate what's the impact of a power price on the cost, electricity cost only of producing a kilogram of hydrogen. Where you see 5.20, it's the cost, approximate cost from, if you want to take it publicly from the web from Hydro-Quebec. It's a Canadian dollar cost, so it should be more like 3-something cents a kilowatt hour US. Your cost per kilogram will go to 2.60. That's just using the efficiency of the electrolyzer at 50 kilowatt hour per kilogram. It's not including any compression if you have to do that for vehicles, filling stations, or the water treatment and all this is not there. But if you look at the price in San Francisco, when it's grid connected price, it's almost 4 times, it's $8.85 a kilogram. And then the next important area is really how clean is the grid. So in the case of Montreal, it's 99.6 clean, so you're producing green and low cost hydrogen. In the case of San Francisco, it's a 32% mix that is renewable. So if you remember, I talked about how the independent power producers can play a role by bringing, having power purchase agreements with low cost renewable power. This is where the market is going to lower the cost of the green molecule.
So Quebec has a lot of clean power, right? So Hydro-Quebec it's a lot of hydropower, so that's the cost is low and it's clean, right? You're not producing power via coal or gas.
Yeah, it's a mostly hydropower, 99 point something hydropower, but that is the picture today. Now, what it's going to be in 5-10 years, you see countries, I read last week in the news that Saudi Arabia signed a contract for $10 a megawatt hour of electricity. That's like 1 cent. Chile is announcing 2 cents or 2 to 3 cents a kilowatt hour. So different economies are having access to very, very low costs of renewable. And this is where you can imagine that markets will pick up into producing low cost clean hydrogen. And you can, and I put that slide, okay, sure, the 20 megawatt is a large plant compared to what's installed currently in the US, but the reality is, I want to make more parallel. Why are the electrolyzers small? Most of them were demonstration projects. There's not that many because actually the power is expensive. And it's just a market that's picking up. And the green dot is one I want to focus on. It's a 5 megawatt electrolyzer that was awarded last year to Cummins. And it's a change in mentality of how utilities work. First, the utility is called Douglas County. It's in East Wenatchee in Washington State. It has access to hydropower from the Columbia River, and it feeds power to its community. It's a nonprofit organization. It really just doesn't mark up transmission distribution. And they're looking at, they have surplus power in some cases and don't know what to do with it and want to monetize that surplus power. So they looked at changing the law, and that law will now allow them to produce and distribute and sell renewable hydrogen. That was not the case before. So they were limited to selling power, but now they can sell hydrogen and have put a request for tender about 2 years ago, 1.5 years ago. And that request of tender was successful. We're very fortunate. And there was a groundbreaking ceremony at that plant, or soon to be plant, about a month ago. We will be producing hydrogen over 2 tons per day. And that hydrogen will be compressed because we're bringing a 2-trailer refueling station. And then the 2 trailers can distribute that hydrogen to customers in the vicinity.
And that power would otherwise go to waste, I assume? Is that?
That's it. But I mean, it's a hydropower. So in some case, they have to let it, to avoid overflow, they have to let it go. But when they have surplus, they can convert that to renewable hydrogen. Hydropower is much more stable. That's the same strength that we have in Quebec. It's really a way to store energy. It's not like wind. It's totally different in what the picture is on that slide in Ontario, where they don't have the same hydropower resources. They've got a nuclear base load. They shut down all coal plants. They have a natural gas fired plants, so that's their base load, and they're putting in lots of renewable wind. But that plant that we've installed a few years ago is going to be blending the hydrogen into the natural gas. But that's one of the things it's doing. But what it is really doing today, it's actually regulating the grid because of all the inputs that come into that electrical network. As I mentioned, wind, solar, you've got nuclear, you've got the natural gas-fired plants, and all these need to be balanced. And our electrolyzer is connected directly to the grid and to the operator of the network. It's called the IESO. And that operator sends us a signal. What you see is, you can't see it very well there, but you have two curves, one superposing the second one. The one behind is the red one, is the signal that we, the signal of the grid operator, and the one in blue is the response from the electrolyzer. I don't know if it'll work, but what you could see is that the electrolyzer on the left axis is the power. It produces, it captures this signal oscillating between 250 kilowatt to 2.7 megawatt. I guess now it was not doing much at that period of time, but at one point you'll see it picks up. And in return for doing that, we get paid by the grid operator because we provide a service, a paid grid service.
So here you're actually matching, if I understand correctly, you're matching power supply, power production with power demand. Normally you have a generator governor changing its output to regulate power output. Instead, you're saying, okay, to the generation facilities, hold your power constant. The load is going up and down, and you're going up and down with the load to stabilize power consumption. Is that, do I have it right?
Exactly it.
Okay.
That's exactly it. And this is a service required there in Ontario. If we make the parallel with the hydropower plant, it's a little bit different. Hydropower plant are more stable, so you can really just close the plant and then let go some water on the sides of that hydro dam. But this is really what we're doing, capturing power, adjusting very quickly to that variation of power, and then producing hydrogen, which will be injected in the natural gas line in the next few weeks. Construction has started, so the pipeline mixing station is being constructed now. Yeah.
So you're creating natural gas from the hydrogen, right?
Right. Yeah. Well, sorry, no. We're producing clean hydrogen, but we're injecting it and mixing it with the natural gas. What comes out of that is lower carbon natural gas. So, and thanks for that comment. In fact, it's on the web how many people will be using that natural gas, in their home for heating or for cooking. And already the council has received a lot of questions. Am I going to get hydrogen in my house? How is it safe? And so we're doing a lot of education, and that's the Enbridge part. That's our customer and joint venture partner, educating the population on the benefits of that cleaner fuel, or cleaner mix, I should say.
I'm going to comment. We have a lot of questions, but I'm going to let you finish
your
presentation. I'll let you finish your presentation first, and then I'll scroll through the questions. Oh, you were done?
Yeah.
Oh, okay. All right. So let me scroll up here and try to find the first question.
Can I remove my share? Yeah.
Yeah. Yep, you can. So there's quite a few questions, and let me see if I can get up high enough here to capture them all. They've been popping in. Okay, so we have maybe you can comment, and some of these are a little bit cryptic for me. So green hydrogen, H2 equals solar. So energy change during the day, hours per day, start-stop times. Perhaps you can talk about that. So I think you're talking about maybe overproduction of green energy during the day and producing hydrogen during that time. I'm not sure about that question.
So I can answer that one two ways. First, yes, you can adapt and start the electrolyzer and take advantage of low-cost, off-peak power, and then produce, low-cost hydrogen as a result, and then turn it off when it's high cost. That's something we can do and match with software. But then you have to find the right application for your hydrogen, and converting it back to power it's a challenging application. It's perfectly possible, and we have fuel cells that can take this hydrogen and produce back power. But this is not the optimal business case. So far, we look more at, as I mentioned, transportation, industry, and other hard to electrify sectors.
Okay. Daniel asked a question, or we're making a statement, I think it's big picture wise, but would it be wiser to develop the hydrogen sector by increasing the network from the bottom up instead of from large hubs top down? That seems to be a costly and far in time.
What do you mean by bottom up?
I don't know. Hydrogen sector by increasing the network from the bottom up instead of from large hubs top down. So I'm not, I might, maybe Dan, if you want to comment again and follow up on that question, we can answer it better. So for Matthew, he's asked, any idea how many megawatt hours of power generation for 1 ton of hydrogen can, well, generation 1 ton of hydrogen can fuel with modern day CT heat rates?
With modern day, so read cut.
So any idea of how many megawatt hours of power generation 1 ton of hydrogen can fuel with modern day CT heat rates?
Oh, 1 ton of hydrogen. I can give you the value, the HHV, the higher heating value of hydrogen, which is 39 kilowatt hours per kilogram. Not to the decimal, 39 kilowatt hour per kilogram. So a ton would be 39,000 kilowatt hour, or 39 megawatt hour per ton.
Okay. Is it possible to use the small size of the system for backup of electrical substations for protection relays and electronic measurement power supplies instead of battery chargers or UPS? So I think they're saying small size systems for backup power.
It's more for backup power. It's again possible if you have you can put a backup generator, a fuel cell generator. And we're working, in the earlier slide, I showed the solid oxide fuel cell that can be a perfect fit as well for that application. But you can also put PEM fuel cells.
Okay. Okay. Where do you see ion exchange membrane water electrolyzers in this product mix and greening of the grid?
The ion exchange membrane is used in our, is that what the question was? It's used in our alkaline electrolyzers. And the proton exchange membrane with the larger scale is it's used in our PEM electrolyzers.
Okay. What's the overall efficiency of the PEM cell when its operation switches between fuel cell mode and electrolysis mode? And does the loop operation affect the cell's lifetime?
So the PEM electrolyzer is one device itself, and the efficiency is in the high 70s, right? Total plant included. But when you look at the fuel cell, this is another device. We're talking PEM fuel cells. This is 50 plus. Efficiency is about 50 plus. If you multiply the two, you'll get to the low 30s for round trip efficiency. If you look, however, at the solid oxide fuel cell, and I encourage to watch the NEPSI Talk 44, I think, with Kevin Harrison. I think he touched base on how high the efficiency was with solid oxide fuel cell because of the temperature, the high temperature, but also heat supplied by another process, which can be almost more efficient. You know, it's extremely efficient. Yeah.
Okay, so LCOH, I'm not sure what that means, but LCOH, could you mention the biggest influential factor? Is it purely electricity cost?
LCOH is levelized cost of hydrogen. And so I like that metrics because it's really what it is. You can buy an electrolyzer for a certain capex, but if you look at all that's required to make this electrolyzer work, you get to the price of a molecule or hydrogen, and that's called LCOH. To lower the cost of hydrogen, the main driver will be power. So, and if power is very, very cheap, then it becomes your capex. So if you have power at zero, for example, then your capex is really the main driver. Other factors, maintenance, will count so little in the equation versus power and capex. However, the benefits of our PEM is that actually there's really little maintenance required. And then finally, it's installation cost. If an electrolyzer is more expensive to install, if it takes 2 or 3 times the size, then you'll add on concrete and building, and that also impacts the LCOH.
Okay, somebody's asking if you've been involved with any projects that have implemented the production of green hydrogen from offshore wind.
Excellent question. This is a market that's there's a lot of lot of efforts made in Europe, a lot of projects being developed to use wind from the North Shore, North Sea, sorry. And in the eastern US, you've got a lot of offshore wind as well. So it is a market that is really starting and has a huge potential, because sometimes you have abandoned oil rigs that can be used as a platform to produce hydrogen. So yeah, it's a good question and a good potential market for sure.
Yeah, this is a good question, I think, too, and it's really a question. Do you think that, are you getting any favorable power prices or tax credits to make this more profitable for organizations to implement, I would think is the question.
Well, today, if you're connected to the grid, I don't know, I cannot talk about all jurisdictions, but typically these rates are rates, if I look at their regulated rates or their negotiated rates with the utilities. In the case of Quebec, and look at the schedule of rates, and there's a power price, so you're charged by the kilowatt, and there's a electricity consumption price and energy cost, which is kilowatt hours, and then the mix of how much power and how much electricity you consume will do that. What I see is that there's a need to relook at how power rates are being put forward. Sure, you can partner with the independent power producer, but in some cases it makes it very challenging to use grid power because of these high distribution and transmission costs. And lastly, because if you're not using your electrolyzer 100% of the time, you'll be hit with a very high power costs. That's the kilowatt or megawatt cost. And you don't use it a lot, so you produce not so many kilograms, but you have the high power costs. And that's not suitable for an electrolyzer. So maybe rethink a little bit how that is done today.
Okay. How does hydrogen compare with battery power storage option?
It is one of the options. We have a battery technology, which is mainly used for mobility, but batteries are a way to store energy. It's an efficient way to store energy as well. Hydrogen will be better if it's for longer term. It all depends. It's a case by case, but they're both solutions to store energy. Batteries have their pros, and hydrogen have their pros as well in some cases.
Yes, there was a lot of YouTube videos out there on that subject I've seen. How long can an electrolyzer operate in standby mode? Do you have a special requirements, depressurizing the stack, etc.?
The number of minutes or hours or days it can stay on standby, I cannot. It depends on some conditions, but the unit is designed to stay pressurized. And at a certain point, if it's been too long, let's say that the controls are active, and let's say there's a power failure, for example, it's been a certain number of hours, well, your UPS battery that's keeping the system not alive for hydrogen production, but alive to safeguard it, like to keep pressure, will then depressurize and safely shut down at a certain point.
Okay. Ramp up time for the electrolyzer, 0 to 100%. Do you have a time period?
It's so from cold, it's minutes. But if you look at what I've shown the slide with the variations, then it's less than a second to go from up to 0% to 100%.
Okay.
It's extremely flexible.
All right. Hydrogen is known to make metals brittle. So do you think we need to replace the existing natural gas pipelines to pump natural gas mixed with hydrogen? And that was talked about a little bit with the NREL presentation.
Yeah, I thought so. I would refer to that. Kevin is an expert in this, Kevin Harrison. But yeah, there's a lot of different types of pipeline. I think he referred to some pipeline even made of not even of composite or steel at one point. And but the material is, yes, hydrogen can embrittle. It's a question of how much you inject, what's the pressure of the pipeline. So there's a lot of research being done by many labs around the world. Some as well are even thinking of re-sleeving pipelines or building an entire new network like it was done. It's a little known fact, but in the refinery areas, there's a lot of hydrogen pipeline. Where I was living in Belgium, in fact, in front of my house was a hydrogen pipeline that Air Liquide had to go to the refineries in Antwerp. So these pipelines exist as well. It's just that the network is not extended to supply other applications than refineries, really.
We're back up to that ramp up and ramp down question. There's a follow-up question to that. Does it affect the lifetime of the electrolyzer?
Actually, the good news is that we don't see that it's a significant impact on the lifetime. Hydrogenics has been established in 1995 as a test fuel cell company. We were making test stands, so we have a lot of background on testing, and we really test these stacks, doing ons and off and various rapid cycling, and degradation has not been an issue with turning on and off. We had a different kind of degradation rate with our alkaline, though, I must say.
Okay. Okay, so there's a question about anion exchange, and I'm sorry, I think I messed up that question prior about ion exchange, and it was really anion exchange.
Yep. Okay. Well, I couldn't hear. We don't have anion exchange now, so I can't really comment on that.
Okay, well that's an easy one then. So, okay, totally. Okay, CapEx, OpEx, we can't answer that. Do you have any idea that?
I can say something about CapEx, though. I mean, I hate just to not answer. What's happening is that the PEM technology is evolving quickly and the CapEx is going down. There's studies out there. You can look at the Hydrogen Council, the independent, the IEA. There's tons of studies on hydrogen and showing, alkaline and PEM CapEx. What's happening is these studies become outdated quickly because the progress that electrolyzer vendors around the world are making on the PEM technologies are very quick. So material costs, catalyst loading, and all these things help drive the CapEx down. The research we're doing and that others are doing too. So,
okay, there's a question about earth. Yeah, there's a question about earthquakes. Electrical grids. Everything's being built earthquake resistant. Can you comment about the electrolyzers?
Yeah, I can. We worked in many areas that have earthquake high seismic rating, high seismic zone. I can name one. You saw it earlier, Colombia for the glass plant. That is in high seismic activity. We have California, of course, that's also high seismic activity. What we do is we design. We design these containers and the shutdown systems to comply with the code, whether it's UBC, I believe, and the zone in effect.
Right. Yeah.
There's a design, and it's taken into account in our design.
Okay. So there's a question from Taz. What's the nature of the power electronics needed to run the electrolyzer? I will refer people back to a prior Tech Talk on that question, just so you're aware of it. Tech Talk number 46 talked about rectifiers and the electrolyzer. But you can also comment if you would like, Michel.
Power electronics are very important. That's how we feed the power to the stacks and control those stacks and protect them from going into overpower or short them or so on. So very important. And as we work and develop other solutions, you can imagine in time we may skip some rectification stage and connect directly to solar, for example, that will require different types of power electronics as well. Okay.
So we're just about getting done here. I will remind everybody, if you're looking for PDH contact certificate, send myself or Matt an email, and we'll use the code H2 today to base on hydrogen, and we'll get you a contact hour certificate. Next week, no Tech Talk. We're going to follow up most likely the following week with a Tech Talk, so we will be with you next week. And we'll go back to Michel. Hey, Michel, I don't see any more questions. Oh, we got one. Floating wind. I'm not sure we're interested in ILOT projects with floating wind. So maybe floating wind projects. But I think we're just about done. We're already at least an hour and 10 minutes in. So I think we're about done. You want to add anything, Michel, before we close up?
Well, I really appreciated the participation and questions and your invitation, Paul. It was a great, I hope I could answer most of the questions and provide valuable information.
Yeah, I appreciate you coming on, and it's a hot topic. We had a lot of participants today with the NREL Hydrogen Tech Talk we had a few weeks ago. Same thing, lots of participation, lots of good questions. So I appreciate you coming on to touch upon the subject, and it's relevant to our industry, as I've indicated, and it's a great initiative going forward for decarbonizing the planet, right?
Thank you very much.
So,
Congratulations for your tech talks. Pretty well
yeah.
done.
All right, great. Thank you. Thank you for coming on.
Looking forward to working with you. Bye.